Today I will be reviewing the practice final exam problems 8 to 15. So starting with number 8, for the given graph, part A, in your own words, for the function shown in the graph below, describe the relationship between the input domain and the output range. So that's the first part of this. So as you can see here, we have a graph. Along the x-axis, we have the length of the race in kilometers, and along the y-axis, we have the pace measured in kilometers per hour. And this is our graph, our line right here. To note, this is from Unit 9B. The formula and example number 2 can be found on page 528 to 529, and that will help you in solving a similar problem. So to start, we first want to do what we did for problem 7 of the practice final. So we want to identify the various variables to determine the domain and range. So we can start by determining that the independent variable, remember it varies independently, so between length of race and pace, the length of the race is the independent variable because it varies independently of the pace. And remember, the domain corresponds to the independent variable. So the domain of the line falls between 0 and 45 kilometers in length. And we know that because when looking at along the x-axis, we see that the line falls between 0 kilometers to 45 kilometers. And this length of race is the independent variable because it varies independently of the pace. And remember, domain corresponds to the independent variable. And now for the dependent variable, by default, it will be the pace. So the pace is the dependent variable because it depends on the length of the race. And remember, range corresponds to the dependent variable. So the range will fall between approximately 20 to 45 kilometers per hour pace. And I've determined that because looking along the y-axis, along the pace, it's approximately, so if we line this up, 20 kilometers per hour to 45 kilometers per hour. So that's the range of the pace. And then, so now that we've identified the different variables, we want to go back to part A. So we're asked, in your own words, for the function shown in the graph below, describe the relationship between the input, the domain, and the output, the range. So remember, our domain we determined as being the 0 to 45 kilometers per length. It corresponds to the independent variable of the length of the race. So this is the length of the race again. And then our range falls between 20 to 45 kilometers per hour pace, and it corresponds to the dependent variable of pace. So as the length of the race increases, the pace decreases. So that would be appropriate for part A. So for part A, as the length of the race increases, the pace decreases. That could be a potential response to part A. And now we move on to part B. So we're told to find the slope of the graph and express it as a rate of change. Be sure to include units. To note, the formula for the rate of change, also known as the slope, is on page 527. So the slope is also known as the rate of change. We have the change in dependent variable over the change in the independent variable. And looking at the graph, I can identify this point here along the y-axis as 0, 45. So that's the y-intercept. And then the x-intercept here, so the change in the dependent variable. And so for the change in independent variable, we need to get another set of another point along the graph. So I'm just going to go with looking at 5 here, right? So if we move up, You see that it falls along here, and that point along the graph looks like 542. So from here, the change in the dependent variable, so the slope is also known as y2 minus y1 over x2 minus x1. So our change in dependent variable is going to be the change in pace. So we can subtract our y values here, 45 minus 42, and we can subtract 0 from 5. Oh, and it is important not to drop the units. So here, our units for pace is going to be kilometers per hour. And down below, the change in independent variable is 0 minus 5. And the units for the length of race is kilometers. And from here, you'll plug this into your calculator. And you can also reduce this prior to plugging into your calculator. So you'll get 3 kilometers per hour over negative 5 kilometers. And so from here, you'll plug that into your calculator. And for the slope, you'll get negative 0.6. I believe this is an approximation. Kilometers per hour over kilometers. So that is your solution for part B. Next, for problem 9, we're told to write an equation for the linear function and use it to answer the given question. So 9, you can rent time on computers at the local copy center for a $5 setup charge and an additional $3 for every 5 minutes. How much time can you rent for $17? So for this problem, you can refer to Unit 9B, Figure 9.13 on page 530 for a very similar problem. In that figure, they graph a line by using an initial value and determining the slope. So you can do that if you have time. However, for this problem, it would probably be more effective to go straight to using the formula that's suggested from this figure. So for this problem, you'll want to use the following formula. So dependent variable is equal to initial value plus, in parentheses, the rate of change multiplied by the independent variable. So that's the formula that you're going to want to use for this. So for us, though, the dependent variable in this problem is going to be cost because it varies depending on time. So cost is our dependent variable, and our initial cost is going to be the initial value plus, in short, plus the change in cost. And the change in cost is the rate of change multiplied by the independent variable, because the independent variable for us is going to be time multiplied by the rate of change, so the change in cost. So we have cost equals initial cost plus the change in cost. For us, we need to determine the cost, how much time we can rent for $17. So our initial cost, though, going back to the original problem, you can rent time on computers at the local copy center for a $5 setup charge and an initial $3 for every 5 minutes. Okay, so our initial cost is $5 plus our change in cost. So remember, our rate of change is going to be $3 for every 5 minutes multiplied by the independent variable of elapsed time. So for cost here, let's assign that variable as R. So the cost, the rate, so R, once simplified, is equal to 5 plus and $3 over 5 minutes, so 3 over 5, that's 0.6, multiplied by elapsed time. So time, we can shorten that as T. So 0.6 times T. So that is our problem. And so how much time can you rent for $17? So if R is equal to $17, so if the rate is $17, we can plug that into our original problem. So we have 17 equals 5 plus 0.06 t, and so we're solving for t, time, right? Because we're asked how much time can you rent for $17? So from here, we can subtract 5 on both sides. So we get 12 equals 0.6t, and then we can divide by 0.6 on both sides to isolate the variable t. And these values will cancel out, and we can interchange the left-hand and right-hand side. So we're left with t is equal to 20 minutes. So 20 minutes is the final answer for problem 9. Next, we are told to solve the equation for the unknown quantity x. So number 10, we have 4 to the power of 3x equals 31. So for this problem, we are going to need to use logs, also known as logarithms. So you can refer to Unit 9C, Algebra with Logs, on page 542. This is going to be very useful in reviewing rules for logarithms. For this problem, we are going to want to take the log of both sides to be able to evaluate the x in the exponent. So we're going to take the log of both sides. Log of 4 to the power of 3x equals log of 31. Okay, and from here, we are going to want to use the following rule. Log 10 x is equal to x log of a. So we can use that log rule. So using that logarithm rule, we can do the following. So we have 3x log 10 log of 4 equals log of 31. So from here, to isolate the variable x, we're going to divide by 3 times log of 4. And again, we'll divide by 3 the log of 4. This will cancel out, the 3's will cancel out. Log of 4 will cancel out, so we're left with x on one side. And we'll plug the right-hand side into the calculator, so log of 31 over 3 times log of 4. And that is approximately 0.83. For problem 11, provide an appropriate response if prices increase at a monthly rate of 0.7%. Use an exponential model to calculate by what percentage they increase in a year. So this problem is similar to Unit 9C example number 4 on page 545. For the following problem, we are going to want to use an exponential model. We're going to want to use the following formula. Q is equal to Q naught times 1 plus R to the power of t. Q is equal to Q naught times 1 plus. So for us, R, the monthly rate, is 0.7%, but we want to convert that to a decimal. So it becomes 0.007 to the power of t. And remember, to convert percentages to decimals, you can divide by 100. And from here, we're going to simplify. So we have, again, Q equals Q naught times 1.007 to the power of t. And for us, t is going to be equal to 12 months, because there are 12 months a year. They ask us to calculate what percentage it will increase in a year. So we have Q equals Q naught times 1.007 to the 12th power. When we evaluate that in the calculator, we will get approximately 1.0873 times Q naught. Okay, and remember, to recap, Q is our price after 1 year, and Q naught is our initial price. We want to find the annual inflation rate. To find the annual inflation rate, we know that the exponential function is represented by 1 plus the annual inflation. So knowing that it's 1 plus the annual inflation, we're going to subtract 1 from 1.0873. And we're going to multiply that by 100%. and the annual inflation rate will be approximately 8.7%. So for problem 12, we're switching gears a little bit. We're told a certain drug is eliminated from the bloodstream exponentially with a half-life of 60 hours. Suppose that a patient receives an initial dose of 10 milligrams of the drug at midnight. How much of the drug is in the patient's blood at noon the next day? For this problem, you'll want to refer to Unit 9C, example number 6 on page 547. We're still talking about exponential models, but now we're switching gears to half-lives. We're going to want to use a different formula. So we're going to use Q equals Q naught times 1/2 to the power of T over time of half-life. Okay, so we're going to substitute the values that we know. We know that the initial dose is 10 milligrams. So Q naught is going to be 10 milligrams multiplied by half-life. Let's solve one thing at a time, but we'll leave time as T. And we know that the time for the half-life is 60 hours over 60. Okay, and to solve for T, the time, we know that the patient was given 10 milligrams of the drug at midnight. So that's 12 a.m. And how much of the drug is in the patient's blood at noon the next day? So 12 p.m. the next day. So it's going to be 12 p.m., so noon minus 12 a.m. And we want to determine how many hours between those times. So that's 12 hours. So little t is going to be 12. So now we have 10 milligrams times 1/2 to the power of 12 over 60. We can simplify the following to 10 milligrams times 1/2 to the power of 1 over 5. And we can plug that into our calculators. And we'll see that Q is approximately 8.71 milligrams. And remember, we're asked how much of the drug is in the patient's blood at noon the next day. So remember, this is our initial dose multiplied by 1/2 times T over T/2. And this formula helps us solve how much of a certain drug was in the patient's system at noon the next day. Because T we solved is the hours between 12 p.m. to 12 a.m., time that we want to figure out how much the patient has in their system versus the initial time that the drug was administered. And then remember T/2, we were given that, the half-life of 60 hours. So you just work through the formula and determine your solution, your unknown. Okay, next we have problem 13. So a certain drug is eliminated from the bloodstream exponentially with a half-life of 12 hours. Suppose that a patient receives an initial dose of 25 milligrams of the drug at midnight. Estimate when the drug concentration will reach 20% of its initial level. This problem is somewhat similar to the last problem. We're going to use the same formula. For this problem, it would be important to solve a similar problem so you can get an idea of how to go about that. So refer to Unit 9C, example number 6, page 547. You're going to want to click on an orange triangle to the left of the example to try solving a similar problem, example 9.C.41. Okay, so you're going to use the following formula. Q is equal to Q naught times 1/2 to the power of T over T/2. So we are going to want to divide by Q naught on both sides. Q naught will cancel out on the right-hand side, and we'll be left with Q over Q naught equals 1/2 to the power of T over T/2. Because we were asked to estimate when the drug concentration will reach 20% of its initial level. Okay, so Q over Q naught is our concentration. So knowing that the concentration will reach 20% of its initial level. So Q over Q naught, 20% converted to a decimal is going to be 0.20 equals 1/2, and we don't know the time. We're asked to estimate the time, but we do know the half-life. So the half-life is 12 hours. Okay, so from here, we're going to use logarithms so that we can determine the variable and the exponent, t. So we're going to take the log of both sides. And from here, we can use the rule. We can apply our logarithm rule, as mentioned prior. So this can become t over 12 times log of 1/2. Okay, and then to isolate the variable t, we're going to want to divide by the log of 1/2 on both sides. Log of 1/2 will cancel out on the right-hand side. And we have, so I'm going to interchange both the left and right-hand side so that we have t on the left-hand side. So we have t over 12 equals log of 0.20 over the log of 1/2. Okay, so from here we're going to want to multiply by 12 on both sides to isolate the variable. Multiply by 12 here. Okay, 12 will cancel out on the left-hand side, and we're left with t is approximately 28 hours, and that's been rounded to the whole number. Remember, that's because we multiplied by 12 on both sides. So you have in your calculator 12 times log of 0.20 divided by log of 1/2 to get approximately 28 hours. For problem 14, we have between 2008 and 2012, the average rate of inflation for a particular country was about 2% per year. If a cart of groceries cost $104 in 2008, what did it cost in 2012? So for this problem, you can refer to Unit 9C, example number 4 on page 545. Okay, we're going to use the following formula. We have Q equals Q0 times 1 plus R to the power of T. And we're going to substitute what we know. So Q0 is going to be the initial cost, grocery cost, in 2008. So that was $104 times 1 plus, so our rate so we're told that the average rate of inflation was about 2% per year. So the average rate of inflation, 2% per year, so that's 0.02 in decimal format to the power of T. And T here is going to be the years between 2012 and 2008. So T will equal 4. Okay, so now we can plug that in to our problem. So we have, again, $104 times 1 plus 0.02 to the power of 4. So we will get approximately, to the nearest cent, $112.57. And we've answered the question. That's the cost in 2012 for a cart of groceries. Now, number 15, we're switching gears. We're moving along to Unit 10C. This problem is similar to example number 1 on page 589. So we're told to find the dimension of the object and state whether or not it is a fractal. So number 15, in measuring the area of the object, when you reduce the length of your ruler by a factor of 6, the number of length elements increases by a factor of 24. If you haven't already reviewed this section, we're going to use the following formula. N equals R to the power of D. So it's important to note that the following. So n is the factor by which the number of elements increases when you shorten the ruler by a reduction factor, r. That explains a little bit of the formula. For this problem, we know the values for n and r. So n, remember, is the factor by which the number of elements increases. So n is going to be 24 because that's the factor that the elements increase. And r is the reduction factor. So the reduction factor is 6. Okay, so we're looking for d, the dimension. So we have n equals r to the power of d. N is equal to 24, and our reduction factor is 6. We're solving for d, the dimension. So because d is an exponent, we are going to use the logs to solve for d. So we're going to take the log of both sides, and we're going to apply our logarithm rule to move the exponent down. So it becomes d log of 6. To isolate the variable d, we're going to divide by log of 6 on both sides. Log of 6 will cancel out the right-hand side. And from here we can interchange left and right-hand side to get the variable on the left-hand side. So we have d equals log of 24 over log of 6. From here you can plug that into your calculator, and the dimension is approximately 1.774. And because the dimension is between 1 and 2, we know that this is a fractal dimension. So that's how you would go about answering this problem. So the fractal dimension definition also states that fractal dimension has some properties that are like length, like 1 dimension, and others that are more like area, 2 dimensions.